Going to do another type of problem about volumes of revolutions, this time with something that's referred to as the washer method. So go ahead and begin by graphing the three functions shown, shade the region bounded by the curves, and just as some added practice, use the definite integral to calculate the area of that shaded region. So I've created the graph here and set up the definite integral that will solve for our shaded red region. The x minus 2x simplifies to 1/2 x. Doing our antiderivative from there, we get 1/4 x squared evaluated from 0 to 8. And plugging 8 into this gives us 1/4 times 64. Plugging 0 in gives you 0. So we find an area of 16. What I want to do next is sketch the shape formed by rotating the shaded region around the x-axis. So just like previously, to get a decent picture of what this looks like when we rotate it, we want to reflect our region over the x-axis and see what it looks like below the x-axis. And then we'll try and imagine what it looks like as we rotate everything around. And so here's the region that gets formed there below. And keep in mind that for each of the points along these graphs, as they rotate around, they're going to form circles. And we can just draw a few of them in to start trying to develop a picture of what this looks like. And we see that with these linear functions, we get another cone. However, we've got this purple cone that's graphed here, and then we see as we start thinking about the circles formed by the blue lines, we get this other cone that's graphed as well. And it's only the region that lies in between the two that's going to be filled in as it rotates around, because we'll notice everything between the blue graph and the x-axis is not part of our shaded region. And so we wind up with these circles that have holes in them. Or you can think of the three-dimensional shape as a cone that has another cone cut out of it. So let's create a sketch of that down here, and let's start talking about how we might find its volume. So we've got this larger outside purple cone, and then we have what appears to be another cone on the inside that has been, you can kind of think of it as been removed from the outside cone. And that is one way we could approach this problem. We could treat it as two separate volumes. We could calculate the volume of the outside cone, and we could then subtract the volume of the inside cone. But I want to think of this slightly differently. Since we've been approaching problems in terms of their cross sections, I want to imagine more precisely the shape that is formed when we slice this thing vertically. And hopefully you recognize that what we're going to create are a set of concentric circles. And the region between the circles is what's going to be shaded. Now this is a shape that's referred to as an annulus, or in this context, it's sometimes called a washer. And we're going to get an infinite number of these stacked up together to form our shape. And if we could find the area of them and add those areas together, we would be able to find this volume. So that means we need to think about the area of this shaded region. Well, we know how to find the area of the outside cone. I'm going to call that R1, the area of the outside, or I said cone circle. The area of that outside circle is pi times radius 1 squared. And we've got this inner circle. We can find its area as well. I'm going to call it lowercase r, say 2, so radius 2. And that area is going to be pi times radius 2 squared. And we're going to find the area of our shaded region by subtracting these two things. Now, just like our problems from the past, those radii, they can be calculated from the original functions. So the radius of our larger circle is based upon the function y is equal to x. And the radius of our smaller circle is based upon the function 1/2 of x. So we find that we could do, in order to find the area of this shaded region, pi times the larger radius squared minus pi times the smaller radius squared. And of course, we want to add all of these things up. So we're going to add them up. And in our particular graph, we're going from 0 to 8. It might be worthwhile to simplify these. So one thing you might notice is that there's a pi on both of these. And so this could be rewritten as pi times x squared minus, let's go ahead and square the 1/2 x, 1/4 x squared. And this pi, since it's just a coefficient, we could pull that out in front. And so let's rewrite this equation over here as pi times the definite integral from 0 to 8 of the difference between our two radii, 3/4 x squared. And now we can just solve the definite integral from here. Go ahead and take a second to finish solving that problem. We'll check to see if we got to the same solution. Hopefully, solving that out, you got 128 pi. So let's just synthesize what we did into a generalized formula. The Washer method is going to apply to any graph in which you have two different functions and the shaded region lies between those functions, and you are rotating that around the x-axis. And we've found that we can solve this area by doing pi times the definite integral from a to b of the larger radius squared minus the smaller radius squared. This allows us to calculate the area of the annulus or washer by subtracting the area of the larger circle and the smaller circle, and then adding those up from a to b. To make this a little bit more specific, using function notation, that's going to be pi times the definite integral from a to b. The larger radius is always going to be whatever the outside or higher function is. We'll call that f of x, minus whatever the lower function, we'll call that g of x squared. And that's a way that we can calculate the volume of revolution using what is known as the Washer method. Between now and class, there are two practice problems here. Try these two practice problems between now and class, and we'll take a look at them together to make sure we understand this approach to finding volumes of rotations.